In this video, we're going to talk about the difference between an SN2 reaction and an SN1 reaction. So what you need to know is that SN2 reactions, they work extremely well with methyl substrates. If you have a methyl or primary substrate, or which is an alkyl halide, predominantly it's going to be an SN2 reaction. If you have a tertiary substrate, predominantly it's going to be an SN1 reaction. Now, here's where it gets a little tricky. Whenever you have a secondary alkyl halide, it can be an SN2 or it can be an SN1. It really depends on what type of solvent that you choose and also the presence of a good nucleophile. So let's say if you use an aprotic solvent whenever you have a secondary alkyl halide. This would be like dimethyl sulfoxide, DMSO. This could be a crown ether. It can be acetone, DMFF. Just DMF. These are aprotic solvents. Like if you look at the structure of acetone, there are no like OH groups or NH groups. Basically, there's no acidic protons. And so that is considered an aprotic solvent. If you have that with a secondary alkyl halide, it's going to favor an SN2 reaction. If you have a protic solvent with a secondary halide, it favors an SN1 reaction. Protic solvents include like water, methanol, ethanol, which can be written as ETOH. These are protic solvents. They contain OH groups, hydrogen bonding groups. They can transfer a hydrogen atom. SN2 reactions occur with no rearrangements. In SN1 reactions, a rearrangement may occur. We're going to go over some examples. SN2 reactions have no carbocation intermediates. Basically, the entire reaction occurs in a single step. So SN2 reactions are considered to be a concerted reaction mechanism. SN1 reactions may occur in 2 or 3 steps. For the SN2 reaction, you have inversion of stereochemistry. So let's say if you started with the R isomer, it's going to flip to S. In an SN1 reaction, if you started with the R isomer, you're going to get a mixture of S and R, both inversion and retention. But it's unequal though. You get more of the inverted product than the retention product. SN2 reactions requires a good nucleophile. As you can see, the rate depends on the concentration of the substrate and the nucleophile. If you double the concentration of the substrate, the rate will double. If you double the concentration of the nucleophile, the rate will double. If you triple both the concentration of the substrate and the nucleophile, 3 times 3 is 9, the rate will increase by a factor of 9. For an SN1 reaction, the nucleophile is not important because it's not in the rate law equation. If you double the concentration of the nucleophile, it has no effect on the rate. The only way to increase the rate of an SN1 reaction is by increasing the concentration of the substrate. Okay, so let's go over some examples. Let's say if we have this particular alkyl halide, and first we're going to react it with water. So is this going to be an SN1 reaction or an SN2 reaction? By the way, E1 reactions occur along with SN1 reactions, but in this video we're just going to focus on the difference between SN2 and SN1. The first thing you need to look at is you need to identify what type of alkyl halide that you have. So analyze the carbon that has the bromine. That carbon is attached to 2 other carbons. So we have a secondary alkyl halide. Now, if it's secondary, it can favor an SN1 or an SN2 reaction. Now, we have water, which is a protic solvent. So this is going to favor an SN1 reaction. Whenever the solvent acts as a nucleophile, you have solvolysis. That's the term that describes that process. So in an SN1 reaction, the first thing that's going to happen, actually before we draw the mechanism, let's identify the major product. Now, notice that the secondary alkyl halide is adjacent to a tertiary carbon. And whenever you see that, if there is a higher substituted carbon next to it, it's going to rearrange. Whenever you add water, you're going to get an alcohol. This is the inverted product. but you can also get the retention product, where the stereochemistry stays the same. So as you can see, you can get a racemic mixture, an unequal racemic mixture, by the way. So that's the SN1 product. Now let's say if we use sodium cyanide with acetone. Acetone is a polar aprotic solvent, and in the presence of a secondary alkyl halide, it's going to favor an SN2 reaction. So SN2 reactions do not rearrange. So therefore, the cyanide is going to add itself to this carbon with inversion of stereochemistry. So the bromine was in the front, now the cyanide group is in the back. But we only get one product instead of two products. We only get the inverted product. So as you can see, that's the difference between an SN1 and an SN2 reaction. So now that we've identified the products, let's go ahead and write the mechanism for those reactions. Let's start with the first one. The first thing that happens is the leaving group leaves for an SN1 reaction. And so we get this secondary carbocation. Now, it's adjacent to a tertiary carbon. And so what's going to happen is you're going to have a hydride shift. This hydrogen is going to glide towards that carbocation. And now we're going to get a tertiary carbocation. And at this point, water will attack it. Now, water can attack from this side, or it can attack from the back. However, the bromide is still somewhere in its solution, close to this side, because that's the front side. And so even though water can attack from both sides, the back side will give you inversion, and the front side will give you retention. However, to get the retention product, water has to go through bromide, and bromide has a partial negative charge. And the oxygen in water is partially negative as well. So water is repelled by that bromide. And so that's why inversion is favored more than retention. It could be like a 60-40 or a 70-30 ratio. It's because of this leaving group. Even though it leaves, it's not very far away from that carbocation, and water has to kind of go around that bromide to get there. But that's why you still get two products though, because when you have a carbocation, the nucleophile can attack from the front or the back, giving you a mixture of stereoisomers. So at this point, we have this product. Whenever oxygen has three bonds, it has a positive formal charge. But we don't have the alcohol yet, so we need to use another water molecule to grab this hydrogen, and then that's going to form a bond. So now we have an alcohol. So in this reaction, there were three steps. The first step was the formation of the carbocation. The second step was the addition of water to the carbocation. And the third step was the removal of this hydrogen. Sometimes you can have a two-step reaction. Other times, like in this case, you can have a three-step reaction. So whenever you have a three-step SN1 reaction, the energy diagram looks like this. Here's the reactants. Then you have your intermediate, your second intermediate, and then your products. So you got reactants, products, your first transition state, the second, and the third. Here's the carbocation intermediate, and here's the point where water adds to the carbocation. Which of these steps is the rate limiting step? Which is the slow step? It turns out the slow step is the first step. It takes a lot of energy to get across this hill. Once you pass that hill, it's very easy to go downhill. So the first step in the SN1 reaction is the slow step, or the rate determining step. Now let's talk about that other mechanism that we discussed, the SN2 mechanism. So here's cyanide. The carbon has a negative charge, so it's nucleophilic. It's going to attack this carbon from the back, and expel the bromine atom. Because it attacks from the back, um, we're going to have inversion of stereochemistry. And because no carbocation intermediate was formed, no rearrangements occurred. And so that's why we get that particular product. The energy diagram for an SN2 reaction looks like this. Because it occurs in a single step, there's only one transition state. Here's the reactants, here's the products. By the way, is this process exothermic or endothermic? What would you say? Notice that the products have less energy than the reactants. Whenever the products have lower energy than the reactants, it's an exothermic reaction. Energy was released. As the reactants went down the energy ladder, they gave away energy. Okay, so now let's try another example. So let's say if you have the chair conformation, and we have chlorocyclohexane. What products would you expect if you add methanol? Well, first, what's the mechanism? We have a secondary alkyl halide, and we have a protic solvent, so we're going to get the SN1 product. However, since we get a racemic mixture, we're going to have an OCH3 group on the axial position and the equatorial position. To get the product, all you got to do is get rid of this hydrogen and write it backwards, OCH3. Remember, when we add water, we got an alcohol, OH, as a product. We took off a hydrogen. So this is an SN1 reaction. Now let's say if you add sodium cyanide. Actually, let's use something different. Let's use sodium iodide in acetone. Well, acetone is a polar aprotic solvent, so this is going to favor an SN2 reaction. So we're only going to get inversion of stereochemistry. Here it's in the axial position, so the iodine is going to be in the equatorial position. By the way, the mechanism for this reaction is a three-step process, and it's very similar to the mechanism that we did with water, just without the carbocation intermediate. But let's go ahead and go through the mechanism for that part. So the first thing that happens is the leaving group leaves. So we get the carbocation, at which point methanol simply adds itself to the carbocation. So now we have an oxygen with a methyl group and a hydrogen, and now it has a positive formal charge and one lone pair instead of two. So now we're going to use another methanol molecule to get rid of that extra hydrogen. And so what we now have is an ether. Okay, so now let's say if you have a tertiary substrate or a tertiary alkyl halide, and let's say if you decide to add sodium iodide with acetone, what's going to happen? Well, because it's tertiary, it's not going to give us an SN2 reaction, even though we have a polar aprotic solvent. So therefore, it has to be SN1. So let's go ahead and jump right into the mechanism. The first thing that's going to happen is the leaving group is going to leave. That's step number one. Then in the second step, the nucleophile, which has a negative charge, combines with the carbocation, and so we get this product. Now this is not a solvolysis reaction because the solvent wasn't the nucleophile, and because the nucleophile had a negative charge instead of having or being neutral like water or methanol was, this is a two-step reaction. So the energy diagram for a two-step SN1 reaction looks like this. The first step is still a slow step. So TS1 has the highest energy level. Here's the reactants, the carbocation intermediate, and here's the products. So it looks like that. It has two energy maximums. So that's the energy diagram for a two-step SN1 reaction versus the three-step one that we talked about earlier. Now let's say if you have a primary alkyl iodide, and let's say if we wish to add water. Is it going to be SN1 or SN2? Well, even though we have a polar protic solvent, we have a primary alkyl halide, so therefore it's going to be an SN2 reaction. Water is going to attack this carbon and expel the iodine group. However, this reaction isn't done. Because we use water as a nucleophile, we need to remove an extra hydrogen, so this reaction actually occurs in 2 steps instead of 1 step. So here's the second step, removal of the hydrogen, and so now we have an alcohol. Anytime you add water, whether if it's SN1 or SN2, you're going to get an alcohol. The only thing is, for an SN2 reaction, there are no rearrangements. So that's it for this video, and thanks for watching.